A rectifier is a pretty common tool in the modular toolbox. It can exist in a standalone module or utility module, such as those made by Doepfer or Mutable Instruments. But if you have a MADS, you can set up a half and full wave rectifier using a duplicated signal from a control voltage such as an LFO. So we're briefly going to talk about what a rectifier does and some common applications for it, both in the real world and in the modular. And then we're going to look at some patch examples of why you would want a rectifier and how you can use it. The main tool we're going to be using is the OR output from the MADS. This output takes all four channels through the bus, and rather than mixing them together like the sum output, will give you the maximum function, or the OR function, which means only the highest voltage from any of those channels will make it out. In addition to this, the OR output only responds to positive voltage per the manual, so it is a rectifier. Imagine, if you will, a typical unassuming sine wave. It has both a positive component and a negative component. What we want to do is reproduce only the positive component. So first let's talk about half-wave rectification. A half-wave rectifier will basically remove the negative component and only leave the positive component. And that's going to look something like this. So if we were to continue this series, this would be half-wave rectification. Half of our wave has been basically gotten rid of. So all we have is the original positive component, but you see these gaps that occur where the negative wave still took place. In order to do that, we could use the MADS OR channel, and that's what we're going to do on the demonstration. And then you'll be able to hear in that section the gaps between these, what will end up being control voltages from our LFO. But what about full wave rectification? How can we accomplish that? Right now what I've done is a merely passable job of refilling in the negative component of this wave. And what we're going to do is invert this wave. We're going to duplicate it, invert it, and plot the same resulting wave over the top. So our dotted wave is the inversion of our first wave. Now, if we just let these play together, they would cancel each other out, right? Because they're out of phase with each other. So when you sum them, they would end up coming out to null. So now let's imagine what happens if we do the same rectifying process where we get rid of all of the negative components, but leave only the positive components. So now we have only the positive components. All the negative is gone, but we have the voltage that doesn't get canceled out due to the phase inversion, and this could be used as our control voltage. It will oscillate twice as fast as the half-wave rectification, but there also won't be any gaps in between the waves. Aside from synthesis and CV control, where could we see these being used? Well, imagine, if you will, you have a 60 Hertz signal, just completely at random. Let's say you have a 60 Hertz signal, a 60 Hertz AC signal, that comes into your house through a plug in the wall. So most of our components work off of DC power, not AC power, but it's much easier to transmit AC power, so what we need is a way to get that AC into DC. So let's say we have this signal and we put our wave through a rectifier as the first part of our power supply. What we can do is use what's called a smoothing capacitor, and what a smoothing capacitor does is it basically slows down the amplitude changes in this sine wave. So I'm going to redraw this and make it a little bit bigger. All right, so that's a little bigger. So there's our fully rectified wave. What we want to do is use a smoothing capacitor to level this out. So let's put it through one capacitor. So that's pretty smooth, but I think we could do better. Let's put it through one more smoothing capacitor. Well, that's pretty smooth, but I bet we could get smoother. Let's put it through yet another smoothing capacitor. You know what? Let's skip ahead. The goal is to put the power, the rectified AC power, through enough capacitors such that it becomes a flat line or DC voltage. And that is in fact what we have here. So this is a power supply that I put together for a small Eurorack skiff. This is a board from Frequency Central. It's a very easy board to build, but you can see all of the 6 large smoothing capacitors up here, and their job is to do exactly what this does. After you have a rectified signal, which happens elsewhere in the circuit, you need these capacitors to smooth it out to transition the AC supply that comes into this power supply to DC, which will then send to our modules. So this is an example you'll find everywhere, but now let's look at some patch examples and see how we would use this on the modular. Okay, for this demonstration we're going to be using both oscillators on the DPO. Oscillator A is set to LFO mode. Oscillator B will be monitoring the final output. We're taking that sound directly. The source we're going to be modulating is the fold control, mostly because the fold control, when it's all the way down, essentially acts like a VCA. So you can turn up the fold control just a little bit, and you start to hear the sine tone before it gets folded. But this middle point, right about here, that's going to be our starting point. So we'll know that we've gone to a negative value because we're going to go down to silence and then come back up, and a positive value because of the change in timbre. Negative value, positive value. We're going to have our LFO going pretty slowly so we can hear these differences clearly. We're going to be using the sine output, which is going to a mult that is just off screen, because what we're going to do, like I said before, is split this or double it to go into 2 channels of maths. So here, let's hear the unrectified or normal LFO signal. So you hear it goes all the way up, and then it goes all the way down to the bottom of the fold control where the signal is completely attenuated. And that's not what we want. What we want is the signal to go back and forth from the center position all the way up without stopping down in the bottom. But first, what we're going to do is half wave rectification. So I'm going to plug the first copy of our signal into channel 2. And channel 2's attenuverter is all the way positive. And then what we're going to do is take the OR output. This cable's kind of in the way. We're going to take the OR output and send that to our fold control. So again, we're going to set that at center. Now you can hear that there's modulation that goes all the way up to the top. So we can duplicate that here. And then there's a gap in time where it doesn't do anything. So that's our half wave rectification. The original positive value is always there, but the negative value has been taken out. So next what we're going to do is take a second copy of our sine wave LFO and put that into channel 3. So channel 3 is set fully negative. Channel 2 is set fully positive. So now we're going to hear the same thing, but it's going to be happening twice as often. So the frequency has effectively doubled. So we have that bouncing ball shape as the negative portion is moved into the positive domain. So if I were to unplug channel 3, you would hear just the original positive portion of the wave. And if we put that in now, we have the same portion. The other application we're going to touch on briefly is AM synthesis. And in a future video, I'll be going over the details of AM synthesis, or amplitude modulation, frequency modulation, and ring modulation. For now, we're just going to touch on AM synthesis as something that you need full wave or half wave rectification for. It's basically the same as using one of your ring modulators, but instead of sending the bipolar signal from your carrier oscillator, you're going to send the unipolar positive only signal going into this input. So we're going to start this patch the same way we did the other patch. Just for the sake of thoroughness, I'll show you that again. So our oscillator output here, and now we're in audio mode, or audio rate frequencies. We're going to mult that and duplicate it and set up a full wave rectifier using maths. So channel 2 is positive, channel 3 is negative, and we're going to be taking the OR output and sending that to our carrier. All right. Next, what we're going to do is take the sine wave output of our second oscillator, in this case oscillator B, and we're going to send that to the input. So in this case, oscillator B is our program, oscillator A is our carrier. So now when I turn this up, you're going to hear something with a lot of overtones. So you can get some really interesting interaction between the two oscillators. What's interesting about AM synthesis as opposed to, say, ring modulation is that the fundamental, so the pitch of oscillator B, or the program, listen to that for a second, lock in on that, that tone will stay present regardless of how I sweep this, which can lead to some very interesting timbres. But that fully rectified wave is a key part of how you get to AM synthesis. Now, there was another demonstration I want to give on AM synthesis because the other night I had a patch that I made up with some really nice chime tones that involved this basic setup using the two oscillators from the DPO, except they were going to the LXD. And I'm going to play that back here while I unpatch this, just so you can hear it, because I think it's a good example of the kind of unique tones you get from AM that you might not get from FM or ring modulation. So there you go. That's how you would set up MADS as a half or full wave rectifier, as well as a few use cases. So hopefully you found this helpful and can find some ways in your own rack to implement a rectifier. Hey, go away. No, get out of here. I'm doing stuff. Come on. Move.